So section 3 is going to deal with CN containing functional groups, and these are generally amines. So CN single bonds are what we're going to talk about now. And so amines are groups containing nitrogen with 3 single bonds joined to either hydrogens or R groups. And the geometry is trigonal pyramidal. Remember that the nitrogen has 4 electron groups around it, except that in this case one of them is a lone pair, so it has 3 bonding groups, giving it a subset of the tetrahedral electron geometry, which is trigonal pyramidal molecular geometry. And these R groups that can be bonded to the amines can be saturated, just normal hydrocarbon chains, or they can be aromatic groups. So amines can have, in this special case for ammonia, 3 hydrogens attached to them, or 1, 2, or 3 R groups attached. And the number of R groups attached to the amine allows us to classify them as either primary, secondary, or tertiary. When we have 1 R group, we classify that as a primary amine, 2 R groups, a secondary amine, and 3 R groups, no hydrogens, is a tertiary amine. Notice in this case, unlike with the alcohol, we are focusing on the groups attached to that heteroatom in the functional group, the nitrogen. How many R groups are attached directly to the nitrogen, whereas classifying alcohols, we look at the carbon bonded to the OH, so the carbon bearing the OH, and decide how many R groups are attached to that carbon. We want to take this time to point out that amines are not amides. They don't have a carbonyl group directly attached to the nitrogen. Here's an amide, nitrogen directly attached to the carbonyl group, and here's an amine. They have no carbonyl group directly attached, so they are completely different functional groups, and their properties are entirely different. And one difference is that an amine can form an ion, whereas an amide cannot. So the non-bonding lone pair in the amine can attract a proton, remember that's just an H+, to form a 4th bond to nitrogen, and we call that an ammonium ion. N with 4 bonds and no lone pairs gets a plus charge. And so this is an ion that's formed when a proton reacts with an amine and the lone pair on the amine. So amines can form ions. If we go back and look at the amide, this lone pair is not reactive because it's next to this carbonyl, so it cannot form an ion. When we name amines, we're going to use the simple naming convention, just like we did with ethers. We're going to treat each R group like a substituent. The name will end in YL. And we will list the substituent names in alphabetical order and follow that up with the word amine. For instance, we have 1 R group on this amine. It is a methyl group, 1 carbon. And so the common name is methylamine. If we have 2 R groups attached, both of which are methyl, we have dimethylamine. And we can also get trimethylamine if there are 3 methyls attached. A common name for an aromatic amine, where we have the nitrogen with 1 R group, that is a benzene ring, that's called aniline. So again, we simply list the substituents in alphabetical order. If they're identical, we use di or tri to indicate 2 or 3 of them, and follow that with amine to form the common name of an amine. Many amines have active biological properties. As we mentioned at the beginning of the chapter, amines derived from plants are called alkaloids. We saw some of those, the opium alkaloids, heroin, codeine, and morphine. Here are some more. Nicotine, that's found in tobacco. It has an amine group right here. This is a tertiary amine. It has 2 R groups and a methyl group. And notice in this case, 2 of the R groups are part of this ring. And even though it's 1 ring, it still counts as 2 R groups because it's 2 different carbons attached to that nitrogen. Here's a very simple structure called conine. It's found in hemlock. This is a secondary amine. Again, 2 different R groups attached to the nitrogen. Even though they are part of 1 ring, they're still considered 2 different carbons attached. And here's an example of cocaine, found in coca leaves. The amine here is a tertiary amine, has a methyl group, and then again 2 R groups, 2 different carbons attached to that nitrogen, part of a multiple ring structure. So these are all called alkaloids because they are amines that are derived from plants. So amines, because they have NH bonds, can easily form hydrogen bonds. Here we see methylamine hydrogen bonding with another molecule of methylamine. The lone pair on nitrogen participates in the hydrogen bond to the hydrogen on a different amine. Remember that hydrogen has a partial positive charge because it's bound to a electronegative element, has a partial negative charge. And so we can form hydrogen bonds between amines, and also this leads to their solubility in water. They can hydrogen bond with water. And these hydrogen bonds will determine physical properties such as boiling point and solubility. Amino acids are molecules that contain both the amino group and the carboxylic acid group. Here's an example of an amino acid. It has an amine group that is protonated. Remember that the lone pair on N can pick up a proton H+, and form 4 bonds to N, making a positive charge. This is an ammonium ion here. Here's a carboxylic acid that has lost its H+, forming a carboxylate anion. And this is the standard form of the amino acid. We've lost the H+ on the acid part. We've gained the H+ on the amine portion. And these are found in all proteins, and we'll discuss these much more in depth later on in our chapter on amino acids and proteins. Okay, so on to a practice problem dealing with epinephrine, also known as adrenaline. It's a hormone secreted when the body is under stress. Illicit drugs that are structurally similar to epinephrine are highly addictive stimulants. For example, methamphetamine is similar in structure, shown here. And pseudoephedrine, which is structurally similar, is a decongestant, and it's sold over the counter in pharmacies. That's one reason you have to show your driver's license and give your address and name when buying Sudafed or generic equivalents of Sudafed. The government wants to limit the amount of pseudoephedrine, this molecule here, purchased by any one individual in the hopes of curtailing the illegal methamphetamine synthesis industry. So, first part of the question asks us to circle and label all of the amine functional groups in these molecules. So remember that an amine has 3 single bonds to it. Some may be hydrogens, some might be R groups, but there are 3 single bonds to the nitrogen. So here's a nitrogen in epinephrine. So the amine functional group is right there. We said that methamphetamine and pseudoephedrine have similar structures, so the amine functional group is found in pretty much the same location on all 3 of these molecules. And they are all secondary amines. So there's 1 H and 2 R groups attached to all of these. They are secondary amines. The next part asks us, in what way is methamphetamine structurally similar to pseudoephedrine? How is it different? Well, we have a benzene ring on the left in both molecules, 2 carbons in a chain and then a nitrogen, 2 carbons in a chain and a nitrogen. We have an H and a methyl on that nitrogen, same in both molecules. And we have this methyl group off of the second carbon on the chain in both molecules. So the only difference is the OH group present in pseudoephedrine. And the method of producing methamphetamine simply involves removing this OH group off of pseudoephedrine to produce methamphetamine. So we can see that these are very similar structures. It's a very simple chemical reaction, if you know what you're doing, to remove this OH group and produce methamphetamine. And that's the main reason that we have to, that the government highly regulates the sale of pseudoephedrine. Clicker question 7-8. Which of the following amines would you expect to have the highest boiling point? Take a look at all 3 of these, decide on how they might hydrogen bond with other amines, and then which one would have the strongest network of hydrogen bonds. That should have the highest boiling point. Okay, so we can see the differences between all 3 of these amines. Butylamine is a primary amine, 2 H's, 1 R group. Diethylamine has 2 R groups and 1 H, it's a secondary amine. And ethyl dimethylamine has 3 R groups attached. And so there are no NH bonds present in ethyl dimethylamine, so a pure sample of this amine would not have any hydrogen bonding ability at all. There are no NH bonds, so that would not be an appropriate answer. The differences between diethylamine and butylamine. Butylamine has 2 NH bonds, diethylamine has 1, so we might infer from that butylamine has more ability to hydrogen bond. It has 2 NH bonds plus the lone pair, as opposed to 1 NH bond and a lone pair in diethylamine. So we might choose B, butylamine, it has the most opportunity for hydrogen bonding. Two NH groups, two NH bonds, and the lone pair. And so if we look at the actual boiling points of these three compounds, we see that indeed butylamine has a boiling point 20 degrees higher than diethylamine, and ethyl dimethylamine has the lowest boiling point. There's no NH bonds present. Even though these amines here have all the same chemical formula, 4 carbons, 1 nitrogen, and the appropriate amount of hydrogens, based on the shape or the design of their structure, butylamine has a much higher boiling point because it has more opportunities for hydrogen bonding.